In part 2 of Module 4, we're going to be talking about some examples of steady-state processes and how we can apply the first law to these processes. And the first type of device that we're going to be looking at are nozzles and diffusers. So a nozzle is defined as a device that increases velocity, so increases V, of a fluid at the expense of pressure. And a diffuser is essentially the opposite of a nozzle. It's a device that increases pressure of a fluid by slowing it down, by slowing the fluid down. And what a nozzle and diffuser look like are the following ways. So a nozzle looks something like this, where we have some flow of air going in and some flow of air going out, and this has a velocity inlet, a velocity at the exit. And we can define our control volume as a control volume that looks something like this. So it encompasses the whole nozzle, and we have some flow in and some flow out. And for a nozzle, we can say that the velocity E is greater than velocity I, and we can also say that the pressure at the exit is less than the pressure at the inlet. The higher the velocity, the lower the pressure. Now, a diffuser is the exact opposite. So a diffuser looks something like this. And this something has the same type of control volume that we're going to use for the analysis, and has a flow going in and a flow going out. And this flow going in is a high velocity flow, and it gets slowed down by the diffusion, by the fact that the area becomes larger. And so we can say that in this case, the velocity at the exit is smaller than the velocity at the inlet, and we can say that the pressure at the exit is now greater than the pressure at the inlet. Okay, so just a little bit of an explanation of how this works. And in a nozzle or diffuser, we have one entrance and one exit. So we know that we have a steady system where m dot in is equal to m dot out. Okay, so the mass flow rate in is equal to the mass flow rate out. We also know that the system has no moving parts, and we'll look at what that means when we look at an example of the system. So without waiting further, we're going to do an example using a nozzle and trying to solve the problem for a nozzle. So we have the example that says steam enters a nozzle at 400 degrees Celsius and 800 kilopascals with a velocity of 10 meters per second. Okay, and we have all this information written right here on the left as well. And leaves at 375 degrees Celsius and 400 kilopascal while losing heat at a rate of 25 kilowatts. Okay, so we're given the heat loss rate. For an inlet area of 800 centimeters squared, determine the velocity and the volume flow rate of the steam at the nozzle exit. Okay, so we're going to have to determine the velocity first and then the volume flow rate. So how are we going to do this? Well, the first thing we can do is we can define all our system boundaries. So we're going to use a control volume analysis on this system here. And we know that the mass in the control volume is a constant, and we also know that the energy in the control volume is also a constant. Okay, so those are the things that we can say because we have a steady flow. We can say that we have steady flow. Now, the other things we know is that it says it's losing heat at a rate of 25 kilowatts. So this Q dot is actually showing, so this Q dot right here is actually showing our heat loss per second. So we're losing heat at 25 kilowatts. And we'll look at that, what that means when we look at the first law. So in order to determine the velocity, we're going to have to analyze the system in two different ways. We're going to look at continuity, which is our mass conservation. And we said that if we call this entrance little I and this exit little e as sort of our points that we're looking at, we essentially have the states at I and E. So we can say that m dot I is equal to m dot E. The mass flow rate in is equal to the mass flow rate out. And we can call it just m dot in general. Now, we now can also write, so that's our continuity equation, and we can expand further on our continuity equation later, but let's look at our first law analysis now. So first law. So our first law for steady state systems states that we have Q dot in minus work boundary out, or just work out, is equal to m dot times HE plus 1/2 VE squared plus G ZE minus HI plus 1/2 VI squared plus G ZI. And if you had more than one inlet or more than one exit, you would just add the terms for the inlets given and the terms for the outlets given. Now we have this equation, and now we can make some assumptions about our system. So the assumptions about our system is that we have a steady system, so that's why we used the first law. But there's another assumption that we can make, and that is that delta PE is equal to 0. Okay, we're assuming that the two systems are on the same level, the entrance and the exit are on the same level, therefore the change in potential energy is 0. Now, can we assume that KE is equal to 0? We can't, because now we have a velocity term given. So because we have a velocity term given, and we're trying to look for velocities, our kinetic energy is not equal to 0. Okay, so we have to keep the velocity term in our equation. Okay, now some of the other assumptions that we can make is that there are no moving parts in our system. What does no moving parts mean? No moving parts means that, if we remember, it means that we have no work. Okay, we have no work and no W dot associated with our system. Nothing is moving, so we have no boundary work. Okay, if the boundary was moving for some reason, then we would have some boundary work, but in this case, we do not. So we can simplify our above equation to say Q dot in is equal to m dot multiplied by HE plus 1/2 VE squared, okay, that's our first term, minus HI plus 1/2 VI squared. And now we can determine the states at I and E to figure out what our values are for what we're looking for. So we're looking for m dot, we don't have the mass flow rate. We're looking for H at the exit. What we're actually looking for is VE squared, so we don't have that. We have VI squared already, so we have that, and we do not have HI. So let's try and figure those out. So we can determine our states now, not by a point in time like state 1 and state 2, but we can actually look at our states at inlet and exit. So we can write state I and state E. Okay, the state at the inlet and the state at the exit. And the state at the inlet, we know that we have Pi is equal to 800 kilopascals. We know the temperature at the inlet as well, which is 400 degrees Celsius. And we know that the velocity I is equal to 10 meters per second. And from this, we can actually figure out what HI would be. So how do we figure this out? We're told in the system, in the question, that we have steam as the working fluid. Steam is the same thing as water. So what equation are we going to use to solve for H? Are we going to use CV delta T or CP delta T? Or are we going to use tables? Since we have water, and for water or R134A we have tables, we are going to use tables. And so that means we're going to look for HI, and we're also going to look for specific volume I just to be complete on our state. And we'll see why we need specific volume I. You could go look for it later on, but we'll see why we need VI. Now, in order to find this value, we're now going to go to our tables and figure out what we have. So let's go to our tables and try and figure out HI and VI. So if we go to table A4 for water or A5, I'm going to start with A5 since we have pressure and temperature. I prefer always starting with pressure to determine if we have a saturated mix, a superheated vapor, or a compressed liquid. So we go to PI, we go to 800 kilopascals, which is the first line on this page. And we know that our temperature is equal to 400 degrees Celsius. Okay, so our temperature is equal to 400 degrees Celsius, which means that T is greater than Tsat, which means we have a superheated vapor. And since it's superheated, we can go to table A6. We get to table A6 and we're going to look for our 800 kilopascal point, which is on the first page, and it's this block right here. And in order to find our H and our V, we're going to go look for 400 degrees Celsius. So we have this term, and we find that our VI is equal to this, and our HI is the third term here. Okay, so we can copy down those values, and it's very easy to solve for. So we have that HI is equal to 3,267.7 kilojoules per kilogram, and VI is equal to 0.38429 meters cubed per kilogram. Okay, so we wrote those points down. Now, in state E, we also have to find HE from our tables. So we can say at state E, we're given that the pressure at the exit is 400 kilopascals, so half the pressure, and we have a T at the exit of 375 degrees Celsius. So we can go to our tables and find HE. So if we go back to our tables, we go back and we look now in table A5 for 400 kilopascals, and we see that temperature is still greater than Tsat. Okay, our Tsat is 143, but our temperature is 375. So we know we have a superheated vapor once again. And we can go to table A6 once again to try and figure out HE. So if we go to table A6, we can go to pressure now of 0.4 megapascals, and we know that our temperature is 375. So we know that our value for HE is going to be between these two values. Okay, so we're going to be able to interpolate between these two values to find the value for temperature is equal to 375. And we actually get a value by doing the interpolation of 3,221.8. Okay, so by interpolation, you can figure it out. So we get that HE is equal to 3,221.8 kilojoules per kilogram. And we can write that we got it by interpolation. We could also find VE if we wanted to, but we actually don't need it, so I'm not going to write it, but that's something that you would see later on in the question. Okay, but so we now have our state I and state E complete for our problem, and we have all the information that we need to solve the rest of the problem. So we found HI, so that's good. So let's write a check mark on HI. We found HE as well. So now all we're left to find is M dot, and then we can rearrange the equation to find VE essentially. So to find the velocity, if we know M dot, we can just rearrange the whole equation and we'll figure it out. Okay, so M dot, how do we find it? Well, we know that M dot in is equal to M dot out. And we had said that our continuity equation says that M dot is equal to rho, and we'll look at the inlet. We know that the inlet is equal to the exit, so that's fine. But we can use the M dot for the inlet, and we know that it's equal to rho I times AI times VI. Or in thermodynamics, we prefer using AI times VI over the specific volume for I. And that's why we found the specific volume for I. Because we know the area of our inlet, is 800 centimeters squared. So 800 centimeters squared is 0.08 meters squared, multiplied by the velocity, 10 meters per second, divided by our specific volume, 0.38429. And we get that the mass flow rate is equal to 2.082 kilograms per second. And this m dot I is equal to m dot E and is equal to just m dot in general. The mass flow rate is constant throughout. We have the same mass flow rate in as a mass flow rate out. And so now we can write the equation out and solve for VE. So let me write the whole equation out and then we'll see how we solve for VE. So first things first, what is Q in? What is our value for Q in? So if we look at our system, we're told that Q dot is equal to 25 kilowatts out of the system. Okay, so we know that we have 25 kilowatts exiting the system every second, essentially, or 20 kilojoules exiting the system every second. So it's losing heat at that rate. So that means that Q dot in is actually a negative because we're losing heat. So Q dot in is equal to minus 25 kilojoules per second, or kilowatts. Okay, it's kilojoules per second or kilowatts, but I'm going to put it in kilojoules for a certain reason. And the reason is because we have minus 25 kilojoules per second multiplied by 2.082 kilograms per second. And then we're going to multiply this by 3,221.8 kilojoules per kilogram plus V2 squared over 2 minus 3,267.7 kilojoules per kilogram plus 10 squared over 2. And we know that the units of velocity squared, is, so let me just finish this bracket here. The units of velocity squared is meters squared per second squared. And the units of this term is kilojoules per kilogram. How are these two equations related to each other? So how does meters squared per second squared and kilojoules per kilogram correlate together? Okay, how do they correlate together, and why does this make sense? So essentially, what we have is with meters squared per second squared, we actually have the equivalent to, this is equivalent to joules per kilogram. Okay, so joules per kilogram is equal to meters squared per second squared. And you can find the derivation for this. It's a very simple derivation. It's just rearranging the units to figure out that we have joules per kilogram. Now, if we have joules per kilogram, that means that we have a discrepancy between our units of the two systems. We need to convert everything to either kilojoules per kilogram or everything to joules per kilogram. We need to keep everything in SI units or everything in consistent units. Since we use kilojoules for most of everything, what we can do is to sort of take into account what is happening. We can say, why don't we convert our velocity term to kilojoules per kilogram? In order to convert it to kilojoules per kilogram, we're going to have to do this. We're going to have to multiply the bottom by 1,000. Okay, this is a very important rule that you're going to use all the time. Okay, so you can even rewrite your standard equation with 2,000 at the bottom instead of 2, accounting for units. So this accounts for units of meters squared per second squared to be equivalent to kilojoules per kilogram. Okay, so that's extremely important, and we need to take that into account. So you need to make sure that your units are correct in your system. Hence why we have to divide the velocity by 1,000. The other way to do it would be to multiply everything by 1,000 and just make it joules per kilogram. But that's more terms to change. You would have to change this term, and this term to get it into joules instead of kilojoules, and then your system would work. The answer to your system would come out to the same. So the result is that if we rearrange the equation, we can get that velocity 2 is equal to 260 meters per second. Okay. Now, the second part of the problem says, now that we know the velocity at both points and we know all the information that we're given, the second part of the problem says to find the volume flow rate at the exit. So it says to find volume flow rate at the exit. So volume flow rate at the exit can be found in the following way. So we know, if we go back to our mass flow rate equation, we know that mass flow rate is equal to rho times AV. And we had also said that V dot, which is our volume flow rate, is equal to AV. So if we're asked to find the volume flow rate at the exit, we can say that volume flow rate at the exit is essentially V dot E is equal to A2 times, AE times VE, and that would be our answer. Now, in order to do that, we need to figure out how to solve for this. So how do we solve for volume flow rate if we don't have the area? So we can say we do not have A2. So we do not have A2 or AE, I mean. We do not have AE, so how do we solve for our volume flow rate? Well, we can say that instead of using the area, we can actually look at our system and say, we know that mass flow rate is equal to density times V dot. And that means that if we rearrange the equation, we can say that V dot is equal to the mass flow rate over the density. Okay? And we can go even further and say that V dot is equal to M dot times V. So that means that we can actually say that the volume flow rate at the exit is just equal to the mass flow rate at the exit multiplied by the specific volume at the exit. And so we can find the specific volume VE at the exit in the same way that we found HE. So we can go to our tables, we have our pressure and temperature, we know that we have a superheated vapor, and then we find VE at the exit by interpolating between 300 and 400 degrees. And we get that VE at the exit is equal to 0.74334 kilojoules per kilogram. And we can now just plug into our values. We know that our mass flow rate at the exit, the mass flow rate at the exit is the same as the mass flow rate at the inlet. So we're left with V dot exit is equal to 2.082 multiplied by 0.74334. And we get a value of 1.55 meters cubed per second. So it makes it pretty easy to solve. Okay. We could have also used a different way of getting there, exactly the same equation, but if we had started with our mass flow rate equation saying that it's equal to AV over specific volume, we know that AV is equal to volume flow rate. So that means that mass flow rate is equal to volume flow rate over specific volume. And by rearranging, you would get that V dot is equal to M dot V. Okay, so multiple ways of getting to the final answer, but just remember that mass flow rate and volume flow rate are very closely related, and you just have to play with the equations and play with the values that you have, and use your tables to find your specific volumes, and then you can solve the problem in that way. So before we go into part 3 of this module, I want to finish off this example problem with explaining how we went from meters squared per second squared to joules per kilogram and why we had to divide our velocity term by 1000 and sort of highlight how this is done. Because in the problem, we sort of defined, okay, we're going to divide by 1000, but we didn't show why. So I'm going to show you why now. So if we have we know that we said in our problem, we said that meters squared per second squared is equivalent to joules per kilogram. Okay, and we said that 1 joule per kilogram is essentially equal to 1 meter squared per second squared. And in order to convert that 1 joule per kilogram to kilojoules per kilogram, we had to say that 1/1000th of this is equivalent to 1/1000th kilojoules per kilogram, and we applied that correction factor. Now, we're going to be using this correction factor a lot, and you can just remember the correction factor, or you can actually understand where it's coming from. So where does it come from? Well, it comes from the following. So if we state that we have 1 joule per kilogram, let's try and figure out the relation between 1 joule per kilogram and meters squared per second squared, and why that is. So we can say that a joule is actually equal to 1 Newton meter. So we can say that 1 joule per kilogram is equal to 1 Newton meter per kilogram. Okay, so that's our first relation. 1 joule is equal to 1 Newton meter per kilogram. And now we're going to convert 1 Newton to the simplest possible form for a Newton, so using completely basic units. So we know that a Newton is a unit of force. So we can say 1 Newton is equal to MA, mass times acceleration, which is kilograms times meters per second squared. Okay, so we have kilograms times meters per second squared. So we can substitute for Newton, we can substitute kilograms times meter per second squared. So we can say that this is equal to 1 kilogram times meter per second squared times what was already there, meters per kilogram. Okay, and so now we have an equation that shows kilograms, meter, second squared, and kilograms at the bottom. And we can see that we have a kilogram on top and a kilogram at the bottom. So we can cancel these two right there. So we're left with meters times meters over second squared, which is equal to meters squared per second squared. So since we know that 1 meter squared per second squared is equal to 1 joule per kilogram, in order to make it work for our equation and to make everything equal, we need to convert it to kilojoules per kilogram. So we can say that 1 kilojoule per kilogram is equal to meters squared per second squared divided by 1000. So that's why in our above equation, in the problem, in our first law, we divided by 1000, just to give you a little bit more of detail on that specific problem. So that concludes part 2 of module 4, and we'll be back in part 3 where we'll discuss turbines and compressors and how they work.